Okay, so the chapter we have today is a fairly short chapter. Um, However, it is content dense, and I'll try to break everything down for you. Um, Particularly seeing as there's sort of a gap, like we haven't covered a lot of chapters in the middle for you guys. Um, so yeah, what okay, so what we've been talking about thus far, and I don't know if you followed along logistic regression, but I can talk about logistic regression a bit during this process. So to start off with, for some background, what I'm showing here is this: for linear regression, we considered this conditional mean as a linear function of x, b naught plus beta x, beta naught plus beta x. For logistic regression, we went one step further and we said, okay, let's consider a logit function of this conditional mean as a linear function of x. And now we're trying to generalize this notion by saying, okay, let's consider any function on the left of this conditional mean of y given x as a linear function of x. And by linear, to reiterate, we mean linear in the parameters, which is, I don't know why it's always seemed counterintuitive to me that you would say linear in parameters as in linear in data or variables. But there, yeah, I'm missing some intuition there, but I'll get back to you on that. I guess, yeah, no mind, I'm not hypothesizing. But yeah, when someone says linear models, they generally mean linear in their parameters. So, generalized linear models and iterative least squares. So we are trying to define in this chapter, we want to define what this generalized linear model means. When you said this G link function, what 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 sort of choices of link function do we have at on hand? Like what can we really place as our link functions, and what trade-offs does that have? At the same time, what this eta of x means, and like how it plays into what we're trying to do. So going back to logistic regression, this is the logistic regression formulation. We have our random variable y, which is now binary. We have binarized the output. Um, we have our x's, which is a real valued p-dimensional set of predictors. And we define this logit function or logistic function as log px upon 1 minus px. Hmm. Hmm. I should probably, yeah. So this is like a probability. This p is basically, yeah, okay, I've written about it. So this p is basically, I should write this is probability of y is equal to 1 given x is equal to x. So this is like a x theta something. Well, I'm not going to complicate things for you. Let's leave it as log p upon 1 minus p, and then you can read the chapter to find out what really this p means. So yeah, um, and we don't need this right now. So anyway, that's some sort of like, this is the formulation for logistic regression, and we are saying that, okay, how do you generalize this notion of a link function, this g, and then this linear model in the predictors? So consider what we did for logistic regression. We want the conditional mean, um, model the probabilities, and again, there was a whole point about why we model the probabilities, and like why we make the probability a function of x as opposed to considering some probability of some data without having it dependent on x. Um, okay, and the other side of it is your linear model, um, which is equal to this g link function, what we're talking about. So We want to solve this problem by finding the right parameter values such that this equation will hold. That is our problem at hand. And we will make certain choices of functions on both sides. What we really have, again, like keep in your mind that this is what you really have. You have sets of y and x. Like this is your data set. And all of this stuff you're building up in your head, and you're saying, I'm going to assume there is this model. I'm going to assume that there are these functions, and like hopefully that holds. And that's very interesting to make those assumptions, but um, yeah, that's what this textbook is like entirely about. I would say, because like you're layering, and he mentions this in one of the chapters, like you're layering so many assumptions one on top of the other that you have to be super careful and cross-examine where each of them fails. So like from x y, you're going to g of mu of x and eta of x. So it's hard, and it's very seldom that you will find everything magically works out, but it does. Because in practice we have good results with just linear and logistic regression. So clearly something is going right. Um, and that going right might just mean two internal mistakes are canceling each other out, which is also a point he gets at. So this question 3.3 that I posted in the chat about is sort of about this idea, and it in the section that it references, it mentions that sometimes you get lucky with sampling, and you get lucky with your assumptions such that the sampling error is negative, and this assumption, the error from the assumption, is positive, and these cancel each other out, and so the net result of that is on that sample your method works very well, and which is again more motivation for you to resample your data, rerun your analysis, calculate standard errors and confidence intervals, and that will really tell you how well you're doing. So again, side note from everything, mainly because this chapter is short and we have time. But I will try to keep it under an hour. Okay. So what is going on now? Now, if you assume this sort of model and you have your data y and x, the simplest thing you're going to do is, okay, let's just apply some function to y and see what happens. But okay, wait, if y is always 0 or 1, then applying this sort of log y upon 1 minus y, 1 minus y will become 0. Division by 0 gives you an error of infinite. Secondly, so this is when y is 1. Suppose y is 0, then this numerator tends to 0, and a numerator becomes 0, and then the value of the g of y is 0. So like this tends between these two terms. Oh, sorry, log 0 is minus infinity. Yeah, log 0 is minus infinity. Just remember your log function or something like that. And so this log 0 goes to minus infinity. So yeah, we have problems like what can we do if we want to start with fitting this model to our data? Well, consider the Taylor expansion at this point, mu x, which is the expected value of y given x. Um, Conditional expectation. But anyway, so Taylor expanded about a particular point of interest and only consider the first order term. So recall that Taylor expansion is this way of using derivatives to say a function has this sort of form in the close vicinity of this particular point. And we're discarding the rest of the terms, saying that their contribution will not be meaningful, which is why first order Taylor expansion. And first order has to do with this thing, this derivative, first derivative. Okay, so the first derivative of this link function times y minus mu x. This y minus mu x is basically the bias at and because like well, I say bias, but like in the limit of a lot of data, you expect that your y uh, given x will converge to mu x, right? And I'm being hand wavy here because like mu x is equal to expectation of y given x, and I guess I'm saying that eventually y will go to its mean and there will be no bias between these two things. But that this entire term is expectation zero. That's all that I'm trying to get at. Um, but yeah, let's leave that out for now. So this Taylor expansion, so we know that g of mu x can be rewritten as eta of x, and we have this other term that is expectation zero. So um, that is why Shalizi claims that this term y minus mu x it acts as the noise. What do you mean by that? Well, you typically assume that you have zero mean uncorrelated noise, right? And in this case, that it acts as this sort of term that varies until you don't have enough data. Once you have enough data, it basically goes to zero because y becomes equal to mu of x. So yeah, so this function, we Taylor expanded it because we were running into these minus infinity and plus infinity errors. We Taylor expanded it, arrived at this formulation z, and we defined this to be our effective response after transformation. So yeah, our z is our effective response after transformation. And if there was no noise, then just regressing this on uh, regressing this entire term on x would give us back exactly the coefficients beta naught and beta. Why? Because, well, eta of x regressed on x will let us know what beta were, because you're saying I have a model. um, this model basically means beta plus, and so it goes back to your linear regression, right? Your y you model as beta naught plus beta x, and you regress y on x to obtain these parameter estimates. So that's all that they're saying here. Okay, I'm maybe I don't think I'm abusing this notation, because this notation is also like simulate or sample, draw, sample, but it's also used to say y regressed. I don't remember exactly, like, never thought about that. Yeah, okay. Anyway, so that is like what we're saying here, that if we could just regress this term, we could get those parameters. And because we're building an estimator, sure, we can do that to get those parameter estimates. Um, but this is all because this expectation zero term leads to unbiased estimates. So I'll pause here for questions for a second, because we've been through a lot of material and there's a lot of background knowledge that you might be missing. So let me know if I need to explain something again.
Hello, Swapnil.
Yeah.
Further, in 12.5, we've taken y minus mu x equal to 0. So I just want to confirm, is it because the mean of the noise is 0, so that's why that doesn't count, and it converges as y equal to mu x, or is it something else?
So right now we're not talking about noise at all. We're saying that the expectation, so y is our random variable of interest, right? X is fixed. Right now this small x means that your notation is capital X is a random variable. Small x is a realization in technical terms. So this is the value that the random variable takes, right? So given a data set of x, we want to model the response y. This is capital Y, right? And the model for the response involves this conditional mean of y at a value of x, which is why this is a function of x. The conditional mean depends on the x values. And so we're saying this random variable y will converge in expectation to its conditional mean given this x. And because if you get a lot of samples, on average, that value will match the conditional mean. Um, I keep saying conditional because your x is given, but really like it is in this setup where x is fixed, your y will go to its mean. That's it. That's all they're saying. And because y goes to its mean, that term will go to zero. So it is similar to a noise term, but it is not a noise term. Like it's acting as if it is a noise term, but it's really just like this first order expansion of the Taylor expansion at mu x. Does
Okay.
this help?
Yeah, yeah, I got it.
Oh, any other questions? Okay, cool. If you have any, feel free to interrupt me because this is like a 6-page chapter, but like he's filled a lot in those 6 pages. Okay, so yeah, this is what I was saying. Like the setup is we have data, we want estimated conditional mean. Our model tells us that we can replace these things. So the link function g of mu x can be replaced by g of y. But since g of y runs into errors, we create this z term using Taylor expansion. And then we have this eta x, which is basically a linear function. And so this is our setup for like our estimates of these values. And what you want to do is you want your estimate to converge to a certain value given all of your data. So first things first, let's examine what is going on here. Like what we said we can model, we can estimate, we can use this first order Taylor expansion to as an estimate of g of mu x. But really, like what is the mean and variance of these terms? And we saw that in it is unbiased, which means mean is equal to eta x. So we're good on that. But what is the variance of this estimator? And the variance of this estimator, so it's like a common theme, right? Whenever you have an estimate and you want to figure out what evaluate the quality of the estimator, you want to calculate its mean and its variance because that reveals what happens when you give it more samples. Does it go to the true value? Is it a systematic distance off? Is there a bias, is what I mean. What is the variance? Is it super high variance? Is it low variance? You typically want low variance estimators because it's nicer to have. In the sense your values are not fluctuating like crazy, so you can inspect it and see some pattern, reasonable um, variance. But that's the idea. So you want to evaluate the quality of your estimate, you find the mean and variance. So your variance of z given x uh, gives you two terms. The variance of the first term that we wrote here, eta of x, plus the variance of the second term that we wrote here. And remember that g dash mu x is a fixed value given x. Hmm, hmm. Shouldn't be right. Hmm, interesting. So it comes outside the expectation because they treat it as a fixed value, but isn't that the conditional mean is not a function anymore because y is a 0, 1 random variable and condition on x. I'm not sure why this comes out exactly. Maybe I'm missing something super simple. Like I've written here fixed given x. Um, But isn't that the expected value of y given x is equal to x and this is a random variable? I wonder. I guess you're saying g is a function that maps certain values of x to a certain value of y. So given a certain x, it will have a deterministic output. So g. to log px upon 1 minus px. I'm sorry, I'm ranting here, but I'm trying to explain this to myself before explaining this to you. So I'm sorry if I end up initially confusing you, but I promise I will make it clearer after I understand it. So this goes back to like conditional expectations of random variables being functions as opposed to scalars. So expected value of a random variable a is a constant, is a mu, right? But conditional expectation of b, a random variable b given a, is a probably like a function of this value of a that it is taking here. And so I was a little confused about like, okay, if you say it's a function, then is this deterministic, or like when you take a variance of this with respect to, never mind, I'm probably confusing you further. Right now, to take the variance of z, we take the variance of two of those terms. We can do that because they are uncorrelated. Um, the variance of the first term, which is essentially a fixed value given x, right? Given x, beta naught plus beta x will be a fixed value. So you have some guesses for your parameters, beta naught and beta. You have your x, which means this term is a fixed value. So yeah, so it has no variance. The second term is really what you will observe has some sort of variance. So g dash mu x comes out, um, that's squared, and then what's remaining is the variance of y given x is equal to x. Right, which means mu x is a constant. Huh. Interesting. Okay. Cool. So this is the remaining term in the variance of this estimator, and I will show you why this is important. But for now, it has two parts. One is the derivative of the link function. So in logistic regression, if your link function is log x, then your derivative is just 1 by x. So this becomes your g dash mu x, right? I'm just using this as an example. You'll come across better ideas before going forward. And this variance of y given x is equal to x depends on like the form of the random variable that we assume. Why does it depend? Because here we have said that let's take y as 0, 1. In logistic, in reality, like y might be real valued, right? But we bin it. We say, okay, we divide y into two intervals. Below this threshold, we'll give 0. Above this threshold, we'll give 1. So it depends on this model that you choose for y that will dictate what your variance of y given x is. So we later come across this, but like I'm just explaining the motivation that we have data, we are placing our assumptions on top of these data, and that will result in this bias variance of the data set. Cool. So that's the variance term from your choice of model for y. And this g dash term is this constant term that he is saying this acts as like a scaling factor. So you know now that the variance of y is a function of x because y given x, right? Which means at different x's, there will be different variances of y, which means that this is now a heteroscedastic regression problem. Any confusion so far? You can ask me to go over things again. I'm more than happy. Okay, seeing none, what we've done is we've now taken this Taylor expanded estimate, examined what quality it has in terms of the mean and variance. We know it has an mean equal to the true value, so we're good with that. That is unbiased. We know that the variance now depends on this choice of y, distribution of y, and this link function, the gradient of the link function. So two factors contributing to this estimator varying. Okay. Um, so if you start thinking about what happens with this in logistic regression, it means that your logit function log of x minus log of 1 minus x. This is essentially what we're saying, right? Because we had log p of 1 minus p. I should write p here. And so this reduces to this, and once we take the derivative of this is 1 by p plus 1 by 1 minus p, which if we add up, this becomes 1 upon p into 1 minus p. So that is what they're writing here. Uh, um, yeah, the derivative of your link function will be 1 by mu x times 1 minus mu x. And so this variance is inversely, the variance of z given x is the square of this times the variance of y. And we have both of these things for logistic regression, which gives us this final variance of mu x times 1 minus mu x inverse. Inverse is important, remember that. And this goes back to the heteroscedastic regression chapter where we said weights have to be inverse of noise. Why? Okay, intuitively think about it this way. I have a bunch of data. At some points, I know that there is a super high variance and I want to fit a model to that data. So naturally, I want to say that like I'm uncomfortable trying to use these points with super high variance in my data set. So I'm like, I will weight them less. How much less? Well, let's just weight them by the inverse of the noise variance. So that is what we do in the heteroscedastic regression chapter. There is this entire algorithm where we first fit a linear model. Then you see how wrong you are at certain points. At some points, you will be more off than other points. So you pick these points where you're more off and you say, okay, I'm very wrong here. So the next time I fit my model and I iteratively refit my model, the next time I fit it, I'm like, I don't want to weight these points very high, and let's see what happens if I do that. Fit a new model. Again, some points you will be very off. Repeat your procedure. I don't want these points. Repeat your procedure. I don't want these points. And by I don't want, you mean you weight them less. How much less? Inverse of noise variance. That's it. That's iteratively reweighted least squares regression. And that similar procedure is what he goes on to describe here, except in this slightly more complex setup where you have a transformation of y and a transformation of x. Well, not a transform of x actually. You transform the response. So that exact procedure is what he describes here. So basically that means your weights are inversely proportional to the variance, right? So your weights will be inversely proportional to 1 by mu x into 1 minus mu x, which means they are proportional to mu x times 1 minus mu x. Everyone clear on this? Especially the motivation for that, because that I can definitely go over again. The iteratively reweighting scheme.
Yeah, it's clear.
Cool. So iteratively reweighted least squares, lots of math here, lots of ideas, but fairly straightforward in terms of like what GLM is really doing. Okay. So this steps back and reviews all of what we did. What we did was we have some sort of linear predictor that we assumed. We have some sort of link function that we assumed. We have some sort of dispersion scale function. I was confused originally because like, firstly, I don't like when people give things complicated names, but I understand the need for them to like name things. So fine. But what this really means is like, what model do you assume for y? That's it. Like this dispersion scale function v mu equal to mu1 minus mu whatever is just this whatever based on what model you assume for y, you arrive at this variance of y given x, which has to do with this g dash times this mu. Basically, this assumption comes from what your assumption on p of y is. In the logistic regression case, we had v mu is equal to mu times 1 minus mu. Wait, wasn't this? Yeah. Okay. With these, we know the conditional mean and the conditional variance of the response for each value of the input variables x. And the exact same setup starts off again. Fix the link function, fix the dispersion scale function, make some initial guesses beta, and then until they converge, just repeat. Fit your model, find the transformed responses, calculate the weights. Wherever the noise variance is high, you want to weight them less, perform your fitting all over again using the new weights, find where your noise variance is high, fit them less, perform the new fitting, so on and so forth until your weights converge. Okay. Um, a nice sanity check for like this whole procedure is to say, okay, but like, does this hold in the case of logistic regression? And it turns out if you assume your noise variance is sigma square, if you assume your link function is just the identity function, then you end up with g dash is equal to 1. That's fair. Variance of y is equal to sigma square. So v mu ends up being 1. Um, Remember that variance of y given x is equal to g dash square times variance times v. So this is 1, this is 1. Oh, sorry, this is sigma squared. No? Right. Uh, wasn't variance of, oh, this was variance of z given x. Oh. Sorry. This is variance of z given x, but variance of y given x is equal to sigma square. Okay, this is fine. Um, cool. And this now has to do with noise variance, right? Cool. So yeah, so if we have this setup, then your response zi is basically equal to yi, and we end up just regressing yi on xi with no weighting at all. So we basically do ordinary least squares because this variance of z given x is equal to this weights, right? Wi. We saw this, and basically we are saying the weights are all one, 1 over 1, which is equal to 1. So yeah, that is a good sanity check to have when you're trying to generalize concepts to more complicated aspects. Cool. Now he takes an example of a generalized linear model and he motivates this as the following. So we selected binary y, now we're looking at binomial y. And why do we look at binomial y? Well, because in some cases we have a lot of trials and we want to model the outcome of those number of trials using some response variable. So your y will be an integer count running between 0 and n. So number of trials could be number of patients in a hospital ward, number of children in a classroom, number of widgets produced by a factory which are defective, number of people in the village with some genetic mutation. Like basically a lot of real life cases involve this binomial random variable. So it is a good thing to use. So the binomial distribution, for those of you who don't remember it, is basically the, I don't want to get into that right now. Just like you perform a series of experiments. Each experiment is independent. Each experiment has a certain probability of success or failure. And this is the model that describes the possible outcomes of those series of experiments. So n trials, success probability pi, and it is a logistic function of predictors x. We do make one assumption here. So one implication is all of these trials is independent conditioned on the predictors. So y1 uh, is independent of y2 given x. Okay, and this might be a good or a bad thing to do. It varies on the setup. So what we're trying to say is something like a student passing a test is independent of any other factors other than teacher quality and average. Sorry, I misrepresented myself. What we're trying to say is one student passing is independent of another student passing, given that they have the same teachers and all of the factors, like that implication. So conditioned on teacher quality and average previous knowledge, they are independent. Okay, this may or may not be a reasonable assumption. It depends on a case-wise basis. Like at some point, there might be other factors, and I won't get into confounders right now, but if you know what confounders are, they are like external factors that affect two things that we haven't modeled, we can't account for. For example, you're modeling the clinics coming to a patient, but you forget that there is some insurance agency that is telling them we won't pay for this. So then it's really not independent. Like the patients with this agency were clearly not going to come to the clinic, whereas the patients from some other agency might. Anyway, it may or may not be a valid assumption. Now, if you extend this binomial case where you have n and you have p, and now you're saying I will extend this number of trials to infinity, but I will have a very low probability for each of these trials. So when you try to do that, you might say this is equal to the mean by n. Um, yeah, I think that's all I want to say. And once you start doing that, your distribution changes to this binomial from this binomial n times n and mu by n into this Poisson distribution of with a parameter mu. And yeah, I'm not going to get into the details of the Poisson distribution other than to say that this is the most important result where your expectation is equal to your variance. That is one of the key properties of this distribution. Look it up, read about it. This is the form of the PDF for that distribution. E raised to minus mu times mu raised to y by y factorial, where y is your random variable. Yeah, y is the realization of your random variable, just if you're being precise. So remember that. So because of this situation that you're extending the binomial to an infinite case and that is giving you a Poisson, that makes the Poisson suitable for modeling counts with no fixed upper limit. Binomial, we said there was a fixed number of trials. At the most, there can be 100 patients in a clinic. But what if we're talking about a city, we're talking about a country, like the world? There is that sort of a finite upper limit still, but like if you're talking about factory producing goods, there is no real upper limit. So anyway, because the variance is equal to the mean, the Poisson regression is always going to be heteroscedastic. Um, which just means like your noise variance will vary. Since mu has to be non-negative because this is a probability, recall this whole probability of y. Never mind. Don't recall this. It's a probability. That's why it can be non-negative. That's why we need a link function, something like log mu. This produces g dash mu is equal to 1 by mu, and therefore your weights, which is equal to the g dash mu times variance of times v. So 1 by mu whole squared into mu is equal to variance of z given x. So this and the inverse of this, sorry, not like that, I should write. So this is equal to 1 by mu, and the inverse of which is equal to the weights, which is equal to mu. So that's, yeah, in shorthand, but very bad shorthand. That's what I'm trying to say. Cool. So weights, W is equal to mu. When the expected count is large, what this means is so is the variance, which normally would reduce the weight put on observations in regression. But in this case, large expected counts also provide more information about the coefficients, so they end up getting increasing weight. I don't have more to say about this, but I would encourage you to spend time thinking about this. Like, what does this mean? What does the expected count mean? For the record, this is the mu. What does this variance being high mean? Variance is equal to the expected count, so it's also equal to mu. Why would it normally reduce the weight put on an observation in regression? This I want you to think about. Okay. What else do I want to say? I want to say that there are certain standardized ways to work out the uncertainty of your coefficient estimates, and you should read about the Pearson correlation because that is of relevance. But other than that, nothing more to say about that. Modeling dispersion. When we pick a family for the conditional distribution of y, we get a predicted conditional variance function, v of mu x. The actual conditional variance function might not actually track this. So what it goes back to this whole point about, look, we have data and we are placing our assumptions from this data into this, where did we go? Into this setup. But all of these are assumptions, so like they might not hold, which means your variance that you are estimating might not actually track the original variance, which leads to over dispersion and under dispersion depending on your problem at hand. And also you are assuming uncorrelated trials, like for a binomial model, for example, we are assuming that each trial is independent conditioned on the x's, but positive correlations might actually lead to a larger variance than you would expect. And so he suggests a technique to handle this, which also has to do with this iterative estimation procedure, where you consider a function phi x that tracks your relationships in your dispersions. So again, like if you don't understand the maths, like go back and think about intuitively what does this mean? Like you're trying to multiply one function with another, saying that this one is not approximating something else very well. So we multiply it with another function and hope that this now will approximate that function really well. So you're increasing the expressiveness such that you're allowing it to model the other one better. And that's how a lot of things in statistics work. Like if your model is not accurate enough, you allow it certain flexibilities, more degrees of freedom to be able to track what you want it to track. And at the end of the day, sure, it's like this hope that, okay, it will actually use that expressiveness. But in a lot of empirical problems, you see that that is actually the case. Like in a lot of machine learning, you design these neural network architectures that you hope model how our brain actually thinks about these things, and it works. And the fact that it works does not mean our model was right. It means that we might have a right model, but it may also mean that we're making two mistakes that cancel each other out and the same setup ends up working out, which is why it fails for some problems and works really well on others. So yeah, like just getting the right result does not mean your model was right necessarily, which is, I guess, the one line takeaway from the entire textbook. But yeah, this for this next part, unless you've done chapter 10, it will be hard to figure out what he's saying. uh, but I guess we did discuss the key algorithm. So this heteroskedasticity, this noise variance, and ignoring some points, giving more weight to other points, that sort of thing is basically how you deal with heteroskedasticity. So what he's saying is like, get this independent estimate of compare the variances, and then regress those on X to get this factor by which you have to multiply the variance from your samples to approximate the true variance. Pause for questions.
Could you repeat what you just said for the latest one?
So what you're saying is you compare the ratio of your estimated variance to the data set and regress that on your X to figure out how bad your estimate is and what factor you need to multiply your estimate by in order to approximate the true variance better.
Yeah.
Cool. This part is a little hard to follow, um, or at least it was a bit hard to follow for me. I think what he's trying to get at is like for every model that you consider, there will be every class of models that you consider, there will be a saturated model. And by saturated, you mean you give one parameter per data point, right? Yeah, one parameter per data point, which means you can, if you see a data set like this, you might actually estimate something super complicated because you have one parameter per data point. Whereas for a linear model, you would probably do something like that. So this complicated model will have the highest likelihood for the data. Um, and so if your model has high likelihood, then this subtraction will result in this deviance is low because this is a fixed value for a particular class of models. So the minute this starts increasing, this will start decreasing. I don't, so the reason I say like it went over my head was because like I don't understand where to use this in practice. Like maybe I haven't done this level of statistical analysis of my models, or maybe I just haven't studied degrees of freedom enough. But he gets at the fact that if our model is correct, then the deviance will generally approach a chi-square distribution asymptotically with n minus p plus 1 degrees of freedom, which has to do with your data dimensionality. I say data dimensions, but I really mean like this W and this trace of W uh, transpose W that we spoke about. Also see section 1.5.3 for more on this, which is ironic because that's the first chapter. Anyway, yeah, he just makes a couple of points of comparing the deviances of different models and ideas about the saturation. This is another section that I didn't entirely understand, but I can walk you through it. Having chosen a family of conditional distributions, it may happen then when you write out your log likelihood of your data, it depends on both the response variables and the coefficients only through the product of y with some transformation of the conditional mean mu hat. So your log likelihood might turn out to be of the form f of yixi plus yi times g of mu hat I plus h of theta. And he's saying in the case of logistic regression, oh, he's given additional reading. I haven't done that. Okay. This shows that the log likelihood can be put in this form. Okay, so for logistic regression, we do have this. Yes, I buy that. In the case of Gaussian conditional distribution for y, which means this assumption of v of mu, like this p of y leads to this choice of v of mu. I think. No, there is some step in the middle and then there is this. But anyway, um, Gaussian conditional distribution, we would have f is equal to minus y square. So f of y is proportional to minus yi square by 2. G of mu is equal to mu hat I when the log likelihood can be written in this form. G is the natural transformation to apply to the conditional mean. That is the natural link function. So what I thought of originally was that this relates to exponential families that we discussed in chapter 11, but again, I'm not sure. So I add question marks there. But anyway, he's trying to compare this iterative least square solution to the maximum likelihood estimate. So that is like this takeaway here, like under certain conditions, I guess the least squares, just like we compared OLS with maximum likelihood estimate, we are trying to compare ILS or iterative least squares into with the maximum likelihood estimate. Yeah, I don't think I have anything more to say about that. This is how GLM works in R. And this is generalized additive model, which is just one slight departure from what you were saying before. We spoke about this G of mu of X very extensively, but we didn't say anything about this eta of X, which we basically let this be beta X. But he's saying that this can actually be more complicated models of X, which are additive. We don't always have to take this. And by additive, I would recommend you read back to the chapter about additive models because there is an entire chapter about it. And there are different ways of defining this, including using kernels. We discussed this backfitting idea, but either way, like replacing that gives us a generalized additive model. So yes, there are some issues. GAMs converge somewhat more slowly than GLMs, but they have less bias and strictly include GLMs as special cases. So some function of x1 plus function of x2 plus function of x3 will include uh, uh, includes this function of x sorry, what we're saying is beta 1 x1 plus beta 2 x2 plus beta 3 x3 is really what we're saying with our GLM, and this is what we're saying with our GAMs. So that's what, yeah, the general idea is that GAMs are a superset of GLMs, but GAMs require the same way like we're comparing parametrics and non-parametrics, that non-parametrics include this set of parametric models, but non-parametrics are harder to fit, need more data, need more time, need more compute. Same way, GAMs are this superset of GLMs, but need more data, need more time, need more compute, whatever. So this general pattern in statistics of fitting more complex models continues. And with that, we come to the end of the chapter. There are only two questions, and they are important questions. So I would highly recommend you read it. Um, they're not like mathematical questions, so you can figure it out without actually knowing the math going on in the chapter. I mean, in a hand way, like, they are mathematical questions, but they motivate you to think. So thinking is really what I want you to do. If you don't work it out, that's fine, but give me like some sort of output to show that you thought about it, or ask me questions that have to do with it, force me to read it and solve the question for you, or like guide you through a solution. But yeah, that's the end of the chapter. I am going to first stop recording.